So good morning. After Herschel and Planck, I think the next big step in terms of a far infrared space mission would be a large cooled space telescope. And given the unfortunate cancellation of Spica and the uncertain status of origins, I think the Millimetron Space Observatory represents the best chance to see a large far infrared telescope in space in the not too distant future. Millimetron is an ambitious space mission supported by the Russian Space Agency. It consists of a 10-meter dish deployable in space and cooled to a very low temperature, less than 10 Kelvin, with a goal of 5 Kelvins. It would have two operation modes, VLBI and single dish, and 3 single dish instruments are foreseen, 1 heterodyne instrument and 2 cameras called SAX and LAX for short wavelengths, essentially the range of wavelengths between 70 and 500 microns, and long wavelengths, longward of 500 micron up to the millimeter range. Following the cancellation of Spica, our group at CEA has been approached to provide the SAX, the short wavelength camera. This project is not only a concept, it's also an ongoing project, and various elements are in a fairly advanced stage. In particular, the development of the antenna, the petals that will be deployed in space. This is being tested in Russia, and as you can see, this is ongoing. Our group has been approached, as I said, and to provide a short wavelength camera that would be based on the work that had been done for B-BOP, for Spica B-BOP, and the instrument that we are envisioning at the moment would have six bands between 70 micron and 500 microns. Essentially the same bands as Herschel, Spire plus Pax. They would observe the sky simultaneously, but not toward the same field of view. But that does not really matter when you map the big regions of the sky by scanning. Of course, central to this instrument is this a new generation of bolometer detectors intrinsically sensitive to polarization that Mark mentioned. The science case for this Millimetron-B-BOP instrument is essentially the same as the one as the case we had prepared for Spica B-BOP, thanks also to the contribution of several PCMI members. There are 4 main science drivers: magnetic fields and star formation in filamentary molecular clouds, the statistical study of magnetized interstellar turbulence, magnetic fields in nearby galaxies, also dust physics, the mechanisms of grain alignment, and the mechanisms leading to polarization. There are also additional science topics, including the possible detection of distant galaxies and detection of polarization from these distant galaxies and the cosmic infrared background. In this short talk, I will concentrate on the first case, magnetic fields in filaments. So I think you agree that air shell imaging has led to kind of revolution in far infrared imaging. In particular, air shell imaging surveys have shown the ubiquitous presence of filamentary structure in galactic molecular clouds. Here you have examples of air shell images from 4 major air shell galactic surveys, and they all show widespread filamentary structure. With Millimetron-B-BOP, we hope to get similar quality images in far infrared dust polarization. At the same time as air shell, Planck polarization data have shown that these interstellar filaments are closely correlated with the distribution of magnetic fields in and the ISM. As mentioned by Mark, what typically is found is that low density filamentary structures are parallel to the field, the large scale field, while dense filamentary structure tend to be perpendicular to the large scale magnetic fields. Moreover, the air shell results have shown that these filaments are closely connected to the star formation process, in the sense that the vast majority of prestellar cores are found to lie in dense molecular filaments above a transition column density corresponding to a visual extinction of about 7, or in terms of mass per unit length of the filament, this is close to the critical mass per unit length of nearly isothermal gravitational cylindrical filamentary structure. And these filaments are resolved by air shell in the nearby cloud, and have a typical transverse size or full half power width of about 0.1 parsec. These overall, the observations support a filament paradigm of star formation, emphasizing the anisotropic growth of structure in the interstellar medium. There are three main steps. In the first steps, large-scale NHD compressive flows driven by expanding shells creates filamentary molecular clouds with typically 0.1 parsec wide filamentary structures. Then the gravity fragments the densest magnetized molecular filaments into prestellar cores. And then the prestellar cores collapse to form protostars and young stellar objects. Of course, the details of this picture are actively debated, and there are many open issues. But after each air shell, it's clear that filaments represent the molecular filaments represent the initial conditions for individual star formation in molecular clouds. So it's extremely important to characterize better the physics of these structures. And clearly, the magnetic field is a key element of this physics. This correlation between the orientation of the filamentary structure and the orientation of the filament, especially the fact that dense star-forming filaments tend to be perpendicular to the large-scale field, suggests that these star-forming structures are formed by accumulation of matter, of interstellar matter, along field lines. But to investigate the role of magnetic fields in the formation of these filaments and in the fragmentation of them into stars eventually, then clearly we need polarimetric imaging studies at much higher resolution than Planck. The problem with Planck is that the resolution is very low, typically 10 arc minutes for polarization data after smoothing the data to get sufficient signal to noise. And this corresponds to typically 0.4 parsec in the nearest star-forming regions. So clearly, the resolution is not sufficient to probe the organization of magnetic field lines inside the 0.1 parsec interior of these molecular filaments at the scales where the fragmentation occurs into prestellar cores occurs. This can be addressed very well with a bigger telescope, such as Millimetron. And this is illustrated on this on the figures that you have at the bottom of the slide, where you can see that these are synthetic polarization maps. These are field lines inferred from synthetic polarization maps, where you see that at the resolution that we will have with a 10-meter dish, you can actually trace the geometry of the field line inside the structures up to 1.5 kiloparsec, in fact. Which is really not possible even in regions like Taurus with Planck. And furthermore, the presence of a temperature gradient inside these filaments, they are typically colder in their interior than in the outer parts, implies that you can that effectively different wavelengths trace different depths inside these structures. Here, the various curves at the bottom right represent what you would see at between 100 and 500 microns, and you see that you at 500 microns you probe much deeper inside the structure, and you can see you can actually trace the magnetic field in the central region. And so in this way, you can expect to discriminate between different between competing models for the dynamical state for the configuration of the magnetic field inside these filaments, and between the models for the dynamical states of these filaments. And in particular, there is an ongoing debate between two plausible models for the magnetic field in these star-forming filaments. Dynamical flow model, where the filaments are essentially believed to be accretion flows onto a nearby hub structure, and the magnetic field is dragged along the flow and takes a V shape inside the filament, and another picture where the filaments are more in quasi-equilibrium, and the field lines are only slightly perturbed inside the interior of the filament and take typically an hourglass shape at the location of the protostellar cores, where you have local collapse. And as you can see, at the resolution of Planck, we cannot distinguish between these models, while with better resolution, of course, this will be possible. The interesting results have been obtained recently with SOFIA Hawk Plus and also Scuba 2 Pol 2. And here is the example of the Serpent South filament that was also shown by Mark, which is highly thermally supercritical, so it's relatively dense. And that's the point. The current polarimeters are limited by sensitivity and dynamic range to this kind of very dense filaments, but nevertheless, interesting results have been obtained for them. In this case, what is seen on large scale from the near-infrared polarization data and also from Planck is that the magnetic field is, again, perpendicular to the long axis of the filaments. But at a smaller scale, SOFIA Hawk Plus was able to resolve the filamentary, the magnetic field inside the interior of the filament, and the data have shown that the magnetic field becomes parallel to the long axis of the filament in qualitative agreement with the dynamical flow picture in this case. Furthermore, estimate of the field strengths could be obtained. And the results show that the magnetic field is actually very significant in this structure, typically close to a critical mass to magnetic flux ratio in the filament. So that means that the magnetic field is actually close to being enough to support the structure against collapse, but of course only in one direction. Another example is provided by our recent SOFIA Hawk Plus study of the famous B211 filament in Taurus, which is not quite as dense, which is close to, which is what I would call thermally transcritical, so in mass per unit length, close to the thermal value of the critical mass per unit length. Only a small part of the filament, of course, could be mapped with SOFIA Hawk Plus. But the results are...
You have a couple minutes left, Philippe.
Sorry?
You have a couple minutes left.
Okay, okay. I'm almost done. So the field, again, at large scale is perpendicular to the filament, while the distribution of magnetic field lines inside the filament is much more disturbed, and the histogram of polarization angles is much broader at small scales inside the filament than in the ambient cloud, showing that in fact, in this case, there is a mixture of magnetic field perpendicular still to the structure inside, or going along the filament. And again, the field strengths that are derived are very significant, and it shows that the magnetic field does play a role in the dynamics of this structure. But these results are nice, but they are actually very limited. And in the same filament, but another slightly different part of the Taurus filament, for instance, Scuba 2 Pol 2 was unable to detect polarization from the filament itself. It could only trace polarization from the cores inside the filament. So that clearly shows, that illustrates that if we want to do extensive studies of these filamentary molecular clouds, to really understand the physics of these structures, this will not be possible with a ground-based telescope. Of course, we can do progress, and we hope to improve upon SCUBA 2.2, for instance, with NICA 2-Pol soon. But to do systematic studies, we will need a space mission, a cool telescope. And I think an instrument like Millimetron-B-BOP would lead to a real revolution in far infrared polarimetric imaging. It would, in particular, it would provide typically three orders of magnitude gain in sensitivity, so 6 orders of magnitude gain in mapping speed for polarimetric imaging compared to SOFIA Hawk Plus. And it would allow us to deliver wide field images in the Herschel range of polarized emission with a signal-to-noise ratio and both intensity and spatial dynamic range comparable to the Herschel images in total intensity at a factor of 3 higher resolution. And the key advantages of such a space mission would be that it would provide a very high spatial dynamic range, and typically a factor of 1,000 in terms of the smallest and longest scales that you are sensitive to, and very high surface brightness sensitivity. So I really think it would be the next step and a big revolution. Thank you very much for your attention.
So there's a question by Vianney. Vianney, you're online? I see you online, but you put a question on the, oh, mic is not working, sorry. So the question by Vianney is it possible to stack the current low spatial resolution polarization along the filament to recover or construct a signal that would support the dynamic flow hypothesis?
Well, it's not really possible to stack polarization observations of different filaments because they may behave differently. So I don't think stacking is an option. Furthermore, only a handful of these filamentary structures have been observed so far. So you cannot do, you don't have statistics. You cannot do stacking.
Oh, he meant stacking along a single filament. So
yes, but as I showed in the example of the Taurus B211 filament observed with SOFIA Hawk Plus, the magnetic field does not have the same orientation at different locations inside the small part that we could map. So if you stack, you will mix a signal. In fact, that's one of the reasons why you need high angular resolution. That when you have a big beam, you mix what is happening in different parts of your beam, and so you are completely fooled. So I don't think this is really possible. Furthermore, we really want to connect the magnetic field in the ambient environment, the atomic medium, and the dense structure to understand the formation of these dense structures.
Okay, Carl had a question.
Yeah, good morning, Philippe.
Hi, Carl. Good morning.
I have actually many questions, but do you know something about the scanning ability which is projected for Millimetron? Because this is a huge structure, right? So you will not be able to do the same things as you do with a Herschel type telescope. Otherwise, you will run out of energy. And then the other thing is B-BOP in the original design, if I remember well, had a spectroscopic capability. Do you plan, or is it planned to keep that up? I unfortunately did not watch Mark's talk, so maybe I missed it.
So on the first point, the scanning speed, that's something that we are discussing with our Russian colleagues. The scanning speed that we are envisaging anyway with B-BOP is something like 10 arcseconds per second. So it's not very high, but nevertheless it would allow you to map big fields. Honestly, I think that 10 arcseconds per second with Millimetron should be feasible. On the second point, B-BOP, in fact, for Spica, B-BOP was not supposed to have spectroscopic capabilities, but it's true that the Russian would like us to add spectroscopic capability to B-BOP, because in their mind, this SAX instrument that they are talking about is both a photometric camera and a spectrometer. This is why what the S at the end means. SAX is short array camera and spectrometer. So it remains to be seen whether we can do some spectroscopy. It would certainly complexify the instrument quite a bit.
So 10 arcseconds per second is, you need then a 1/f characteristic of your detectors, which is way below 1 Hertz in order to see structures or integrate on structures which are, let's say, 1 arc minute. Which still is something you are interested in.
Yes, of course. So
I'm pretty skeptical about this number. I think you will have.
Sorry, Carl, you are skeptical about 10 arc seconds.
I am skeptical whether you can do a good job with 10 arc seconds per second.
Well, just scaling from Herschel. With Herschel, we were doing 60 arcseconds per second, sometimes less than that. And with Spire, you were really sensitive to this. You really add this huge spatial dynamic range. So you are sensitive essentially to structures up to the scale of your map. With when you were doing a power spectrum, you were not losing any emission essentially up to almost the scale of your scans. So I mean, we can debate about exactly which range of scales you would be able to reconstruct, but I think that's a big advantage of doing this from space, is that you don't have the atmosphere to fight against. And so I think the dynamic range will be much better than from the ground, no matter what.
Okay, thank you very much.